Okay, hi everybody, it's Jeff here. I mentioned in class that I was going to post a video to talk about good style and good commenting in your assembly language programs. We've already talked about the fact that good style and good commenting is important in any language really, but especially in assembly language because assembly language can be quite cryptic. So over the next few minutes we'll talk about elements of good style that you'll be expected to incorporate into your own assembly language programs. So, one thing that we're going to be doing is making use of macros to fill in for register names and to fill in for magic numbers. So rather than typing something like move L0 into O0 or move L1 into O1, and rather than having to mentally keep track in our heads that, okay, L0 maybe represents the user's age and L1 maybe represents the user's birth year. So rather than having to keep track of those facts in our heads when we're maybe writing assembly language programs that are several hundred lines long, we're instead going to use macros that will help to remind us what each register represents. So I might use instead move user age R into O0 or move birth year into O1. Okay, so I'm just giving these register names symbolic names so that, again, it just reminds me when I'm reading this code that, okay, yeah, this register stores the user's age, this register stores the user's birth year, rather than something like this where, what does L0 represent again? I can't remember. Okay, so it just makes your program easier to follow, easier to read, and it'll actually help you. If you're writing some code and maybe you leave it for a few days and come back to it, it'll help to remind you that, okay, yeah, this represents the user's age, rather than, if you just had L0 here, what did I store in there again? Okay, so that's one of the reasons why we use macros. Similarly for constants, rather than having something like move 5 into O0 or move 10 into O1, we'll be using constants. So I'll say something like move initial value into O0 or move the end of line character into O1. Some sort of symbolic name that describes that number rather than just having some magic number that really means nothing in our code. So over the next few minutes we will take a look at how to use macros in our assembly language programs. But before we do, I just want to take a look at macros in general outside of assembly language. So I'm going to create a file called macro.txt. It doesn't matter what I call this file, I'll just happen to name it macro.txt. So what is a macro? Well, a macro is simply a symbol which stands for a piece of text, so that symbol could be an abbreviation. For example, we might have define CSD to be the Computer Science Department. Alright, so this is called a macro definition. I've used the define keyword, and this is the macro, and this is what the macro will expand to. So I've now defined a macro. How do I call the macro? Well, to call a macro, we simply use it. So I could say something like, I really like the CSD. So I've just called the macro there. And now the next question is, all right, we've called the macro, we've defined the macro. How do we actually get the macro to expand? What we have to do is run it through what we call a macro processor. And on Unix, that macro processor is called M4. So I'm going to save this file here. This file I saved as macro.txt. And so I'm going to run macro.txt through the M4 macro processor. And you can see now that my define is gone. That just results in a blank line. And anywhere that it found a macro that was defined, it expanded it. So here it expanded CSD to Computer Science Department. Taking another example here, I could maybe define A to be 65, and then I could maybe say something like the ASCII value for A is A. And running that again through the macro processor, we get the ASCII value for 65 is 65. Now that's not exactly what we wanted here. We wanted it to say the ASCII value for A is 65. So how do we do that? These are both macros because we've defined them to be macros up here. Well, what we can do is tell M4 that we don't want a particular macro to be processed by escaping it between a backtick and an apostrophe. Alright, so now if I save that and I run that through M4, you can see that we get what we would expect. The ASCII value for A is 65. Now we can also define macros to accept arguments. So I could maybe define a macro called sec to be section $1 $2. And maybe I'll just say sec1 is introduction, sec2 is maybe results, and sec3 is conclusion. And now if I save that and I run that through M4, you can see now that I get section 1 dash introduction, section 2 dash results, and so on. So this $1 represents the first argument that was passed to the macro, in this case 1, 2, or 3, and $2 represents the second argument, in this case introduction, results, or conclusion. So there's a lot of neat things you can do with M4. We're really only going to be scratching the surface of it, but I do encourage you to check it out online. There's a lot of good M4 references out there, and there's really a lot you can do with it. Now, before I get into how we're going to use macros in our assembly language programs, I want to show you one other use of M4 because I think it's kind of neat. So let's say that I want to build a web page, or I want to build a set of web pages, and I want to make it a little bit easier for myself. Well, what I've done here is I've created two macros. One's called header, one is called footer. So the header will produce the header elements for a web page. So we've got the HTML tag here, we've got the head tag here, we've got the title tag, and you can see that it takes an argument. So whatever I pass to the header macro is going to be the title for my web page. And then we end the head and we start the body. All right, and then we have a footer macro that just ends the body and ends the HTML page. So I could create, let's say, html.m, and I could maybe say something like header CS2208 sample page, and now we're in the body because the header started the body here. So after we've called header, the body's already been started. So I'll just say something like, I really like CS2208, and then we'll just have our footer. Now if I save that and I run that through M4, you can see that nothing has changed. And why is that? Well, if we take a look at M4, we didn't define that header macro and that footer macro within that file. So what we have to do is actually include that. So I've put those macros in a file called html_macros.m. So I can just simply say include html_macros.m, and now if we run that through M4, you can see that it generated my web page for me. I've got my HTML, my head, my title. So the title of the page is whatever I passed into the header macro, and then we have the body of the page followed by the footer macro. Pretty neat. Okay, so now that we've seen a couple uses of M4, let's take a look at how we're going to apply it to assembly language. So I'm going to open up this file sum.m. First of all, you're going to notice that I'm putting my code into a file with a .m extension. In the assembly language programs that we've looked at so far, we've been putting all of our code in .s files. But when we're using macros, particularly when we're using M4 macros, we're going to put all of our code in .m files to signify that those files contain macros that first need to be expanded by M4 before we can actually go and assemble them. So let's see how I've used macros in this particular file. So you can see here that I've got a few defines. I've got define EOL to be 10, so define the end of line character to be 10. And then I've also got a few register defines here. Define op1_r to be register L0. Define op2_r to be register L1. So if we take a look through the code, rather than using %L0, I'm going to use %op1_r. Rather than using L1, I'm going to use %op2_r. And similarly, rather than using the end of line character, rather than just simply typing in 10, I would say move EOL into O0. So it just makes the code a lot nicer to read. You don't have to remember that L0 represents operand 1. You've got a label here that specifically tells you what it contains. It describes the contents of the register. So again, what I'm doing here is just saying define whatever the macro name is, and then what it expands to. Now by convention for registers, what we do is we append the suffix _r, and that just sort of reminds us that it's a register. Alright, so make sure that you have _r as your suffix when you're defining a macro for a register. Similarly, you're going to notice here that I didn't say define op1_r to be %L0. Okay, and I did not say %L1 for op2r. Instead, I just say define it as L0, define it as L1, and then I put the % down when I actually call the macro. So I'll say %op1_r. A lot of people often do this. They'll put the % in the macro, And then in the assembly language, when they're actually calling it, they'll just simply say something like move O0 into op1R. I don't like that because it's less explicit that you're using a register. I like having the percent outside of the macro because it just seems to make it a little bit more explicit that yes, we are using a register here. All right, so make sure that you have the percent outside of the macro definition. It's just a convention we're going to use in this course. Now you can see here in the code that I've put all of my defines at the top of the file. So I have some sort of header comment at the top of the file that we'll talk about that in a little bit. And then I have my defines, and then my program actually starts. Now you can see here that I've used block comments. I've separated my defines into constants and into registers. You don't have to do that. I just think it makes it look a little nicer. Sometimes we have quite a few register definitions, we have quite a few constant definitions, so I think it just makes it look nicer by breaking it up into two different sections like that, but you can do it however you like. So we've used macros in our code. How do we actually go and assemble this program? So let's take a look at that. So first of all, if I try running this through GCC, if I try to assemble this program, I'll say sum.m and iofunc.o. It doesn't even know what a .m file is. It thinks the .m file is Objective-C. Okay, if I were to try to assemble that file, the assembler has no idea what define means, okay, because define is a keyword for M4. It's not a keyword for the assembler. So you first have to run your code through M4 and then you can assemble it. So let's do that. We'll say M4 sum.m. Now if I just run that, it just prints it out to the screen. You can see that it got rid of the constant definitions, it got rid of the register definitions. And anywhere where I used %op1_r, it changed it to L0. Anywhere that I used %op2_r, it changed it to L1, and so on. Anywhere that I used EOL, it changed it to 10. All right, so it expanded all of those macros. But simply by running it through M4, we haven't done anything. We haven't created a new file. So what you actually have to do is take that output and redirect it to a new file. So I'm going to run it through M4. I'm going to run sum.m through M4, and I'm going to redirect its output to sum.s, an assembly language file. And now if we look at sum.s, we can see that the output of M4 is now contained within that file. And now we can take that file and we can actually assemble it. So I'll say GCC, let's output an executable called sum, and we'll do that by assembling sum.s and linking it together with iofunc.o. And now if I run my program, we can see that it works. It asks us for two numbers and it prints out the sum of those numbers. Now, if I wanted to run M4 a second time, if I said M4 sum.m to sum.s, you can see that it tells me that the file already exists. This is basically a safety feature on Gall that just prevents you from accidentally overwriting one of your files. So we have two options in this case. First of all, we could simply delete sum.s and run it again. Alternatively, we could say run it through M4 and then force it to overwrite sum.s. So by saying greater than exclamation mark, that's just telling it that yes, I do want to overwrite that file. And then you can go and assemble that file using GCC. Now, one thing you may have noticed in the code was that I did not give macro names to the output registers. I'm still using O0 in here. I guess that's the only output register I'm using here, but I don't assign a macro to that. I'm only assigning macros to the local registers, okay? So that is something that you should definitely be doing in your programs. You should not be assigning any sort of macros to any registers other than the local registers. Okay, so just keep that in mind. Alright, so that takes care of macros. You will be expected to be using macros in your programs, and you should be handing in your .m files, not your .s files. We're not interested in seeing your .s files because when we go to mark your assignments, we will run M4 on your .m files and we will assemble your .s, the resulting .s files. Okay, so just hand in your .m files. Okay, so that takes care of macros. Let's talk now about some good elements of programming style. Take a look at the spacing in this program, and we'll compare it now to our sum.m file here. Take a look at this code, and now take a look at this code. Okay, you can see that this is a lot easier to follow. We don't have our spacing all over the place here. We've got our labels in the first column, we've got our opcodes in the next column, our operands in the next column, and then we've got all of our comments lined up. Okay, so you can just, if you compare the two, you can see that this one is a lot nicer to read. It's a lot easier for us to follow. So you will be expected to be using good spacing in your programs. Again, you have your labels, then you tab in, you have your opcodes, tab in again, you have your operands, and then you have a few tabs and you line up all of your comments in the right column. Alright, so just make sure that you pay attention to your spacing. Now let's talk about white space as well. So take a look at this code and then compare it to this code here. Okay, you can see that this code is a lot more dense. It's a lot harder to follow because we don't have any blank lines in here. We don't have any white space. So what you want to do is you want to separate logical ideas in your program by white space. And what I mean by an idea is that in these 2 lines of code, we're displaying the prompt for the user. In these 3 lines, we're reading the first number from the user, and then we're displaying the prompt again to the user and reading the next number from the user. Each of these are separate ideas, if you will, in the code, and each idea should be separated by a blank line, and that just helps to divide up the code a little bit visually so that it makes it easier to follow. Okay, it's not as dense as if you have something like this where it's just a whole big slew of code. Alright, so make sure that you're dividing your code up into logical ideas. And as a rule of thumb, an idea is generally not longer than about 3 to 5 lines of assembly code. That's not a hard, fast rule, but that's just a good rule of thumb to follow. Alright, let's talk about labels. We've already talked about labels as being identifiers for locations of instructions. So for example, here we've got label 1, which identifies the location of this move instruction, and label 2 identifies the location of this move instruction. And so we can reference labels in, say, branch instructions. So I could say something like branch always to label 1, or branch if not equal to 0 to label 2, or something like that. Now, these labels here are not good examples of labels because they don't tell us anything about what's going on in the code. So this label here should really tell me, it should give me a brief description about what's going to happen in this next section of code that starts with this label. And same with label 2 here. This should tell me what's going to happen in this next section of code. So not very descriptive names. These are not the kind of label names we want to be using. Taking a look at a better example, here we've replaced label 1 and label 2 with output multiplication result and continue after output. These are better in that they give us some information, but the thing is that a label name should reflect the purpose of the code that's going to follow it, but it shouldn't be so long that it becomes an essay. Okay, it should be long enough to be meaningful, but not so long that it makes the code wordy and difficult to read. So a better example here would be something like just as simple as print result and continue. Okay, these are descriptive, but they're not overly wordy. So just make sure that your label names are chosen well so that they are descriptive but not overly long. The last thing that I want to touch on is commenting. So again, commenting is very important in assembly language because assembly can be cryptic. So we want to make sure that we have great comments. The first thing that you'll be expected to have is a header comment at the top of your file. Generally, you'll have something like the file name, what assignment it is, what your name is, and then you'll have a brief description of the program, what it's doing, and then you'll have a register legend. So the register legend gives you the mapping between the macro names and the actual register names, and then it also gives you a description of what that register is being used for. Alright, so L0 is mapped to macro op1_r, and it represents the first operand in the addition. Now, for some reason, in all the times that I have been involved with this course, people really have trouble with the register legend. Often what they'll do is they'll just put something like op1_r is the first operand in the addition, but they won't say what the actual register is that op1_ maps to. Or sometimes what people will do is they'll say L0 is the first operand in the addition, but they won't say what macro is assigned to L0. So just make sure that when you're doing your register legends, you have these 3 parts: what the macro is, what the actual register name is, and then a brief description of what that register is being used for. Now you can see that again I've commented these constant sections and the register section just with these block comments. You don't have to do that. I just like the way it looks. But it is very common to have block comments throughout your code that will just sort of describe what's going to happen in the next chunk of code. Okay, so that is certainly a very common thing to do. Now, let's talk about line-by-line comments. You can see here that pretty much every line has been commented. It's not an explicit rule that every single line in your code has to be commented, but I should be able to look down the right column, and without even looking at your code, I really should be able to follow what's going on in your algorithm just by looking at these comments. All right, now, again, we've talked about this in class. A lot of people will do something like this. They'll say move L0 into L1, and then they'll give a comment that says move L0 into L1. Again, I know that the statement move L0, L1 means that you're moving L0 into L1. I'm an assembly language programmer, I understand that. So when you give me a comment like this, it's just redundant. It doesn't tell me anything. You're just repeating what the code says. So don't explain what you're doing, explain why you're doing it. Explain the intent of the instruction. So, you know, maybe something like store the result of the computation. Okay, something descriptive. You don't want to write an essay, but you do want to be descriptive, and you want to make sure, again, that someone can just look down through your comments and understand what's going on in your program. So whenever you're unsure as to, you know, do I have enough comments in my code, just do that exercise. Look down this column and ask yourself, can I follow what's going on in my code just by reading these comments? Now you'll notice here that every time I have filled a delay slot with a useful instruction. So here I have call write char, and in the delay slot I'm moving the prompt character into the output register before write char actually gets executed. So I've filled the delay slot with a useful instruction, and whenever I do that, I put a comment saying just delay slot, something to let me know, to remind myself that yes, I have intended to fill the delay slot. I didn't just forget to put a NOP in there, a no operation. Okay, and it also allows us to be able to see that as well, that you didn't just forget to put your NOP in there. So just make sure whenever you fill a delay slot, have a little note here that says delay slot or something similar. If you prefer, you could just do something like DS if you want, whatever you prefer. Now, if you take a look on the course website, if you go under the assignments header and you click on commenting guidelines, you'll see a detailed description of how your program should be commented. So it just goes into more detail on what I've just talked about, talking about the file header comments that you should have. It gives another example here. Once we get into functions, and you'll be writing your own functions in later assignments, you'll also have to have function header comments, which it describes here. And then it talks about good line-by-line comments, talks about block comments, which I just touched on a few minutes ago, talks about commenting your delay slots. So basically, just goes into more detail on what I've just been talking about. So do have a look at this and make sure that you incorporate good commenting into your programs. Okay, I think that wraps it up. I apologize for the length of the video, but hopefully now you're empowered to go out and write assembly language programs that have great style, great commenting, and you'll all get 100%. All right, thanks for watching.